We're going to look at the properties of alcohols and phenols, both the acid-base characters and some other properties that they have. The first thing that you need to realize is that alcohols can hydrogen bond to each other. Let's look at an alcohol group down here, and you can see there's a large dipole on the hydroxyl group, del positive on the hydrogen, del negative on the oxygen. And these are very small atoms, so they can hydrogen bond to each other. And this is very much like what water does to itself. And alcohols can hydrogen bond to water. So this characteristic is important because it increases both the boiling point and melting point. This increase is very large for small molecules, something like ethanol. It has a molar mass of about propane, whereas propane's boiling point is way below 0, and ethanol actually has a boiling point of about 80 degrees Celsius. So there is a huge impact due to this hydrogen bonding between the alcohol groups. The alcohol group also allows it to be pulled into water by hydrogen bonding to water. The carbon-hydrogen portion of alcohols is very hydrophobic and does not like to be pulled into water. However, the hydrogen bonding hydroxyl, the strength of the hydrogen bonding through the alcohol group to water is so strong that ethanol basically is soluble in water in all proportions. The term for that is miscible in both methanol and ethanol, and even two, propanol, are miscible in water, and so you can dissolve them in water in all proportions. Well, as you start adding carbons on, of course, the solubility starts dropping, and something like butanol has limited water solubility because of the hydrophobic character of the 4 carbons. But it's still the amount of water solubility that you have for something like 4-butanol compared to butane is very different because of the hydrophilic character of that alcohol group. Alcohols are both slightly basic and slightly acidic. The non-bonding pair on an alcohol can be protonated by a strong acid. And we've already learned that when that occurs, it makes the water, the water molecule that results, the protonated alcohol group, becomes a very good leaving group that leaves as water. And we've seen that in mechanisms. So we know that the protonation of an alcohol is possible with a strong acid, and that's because it is a weak base. Phenols also can be protonated with strong acids. Of course, they cannot leave a benzene ring like you can from an alcohol, but they still can be protonated. The alcohol group can act as an acid also because it can lose its proton. For instance, in water there is a very, very slight process of water deprotonating an alcohol. The water acts as a base, removes a proton from the alcohol. However, this equilibrium lies far to the left. Okay, it lies slightly less far to the left with a phenol, but it still is far to the left with phenol in plain water. But you can see right here they're acting as acids by being deprotonated. You can see how weak the acids are. If you look at the pKa of alcohols, they're very, very weak. They're weaker acids than water, except for methanol, which is just slightly more acidic. We'll look at putting electronegative groups on alcohols and how it affects them in just a few slides. But if we look at phenols, you can see they're slightly more acidic than alcohols because the pKa is getting lower. And you can refer back to this table sometime when you might be saying, what is the acidity of this or that, to try and help yourself understand something. Methanol and ethanol, they're about as acidic as water, but something interesting to note is the more alkyl groups that you put on a carbon that has an alcohol group on it, the less acidic that alcohol is. Let's go ahead and look at this T-butyl, the T-butoxide. There would be a negative charge on this oxygen here. Remember that alkyl groups will stabilize a positive charge on a carbon because the electrons that are in the carbon-hydrogen bonds can feed into that positive charge. Likewise, an alkyl group can feed electrons over to this carbon-oxygen bond. That's going to make that negative charge on the oxygen destabilized. That hyperconjugation actually causes this negative charge here on this oxygen to be less stabilized. So the T-butanol alcohol is actually less acidic than methanol. The methanol has a pKa of 15.54 and T-butanol has a pKa of 18. So T-butanol is less acidic than methanol, and it's all because of the hyperconjugation of these alkyl groups. Another way that we say this is we say that alkyl groups are electron donating, and so it destabilizes the negative charge when a proton leaves. It makes that alcohol group less acidic. However, if we have electron withdrawing groups, we can make it more acidic. Here is that T-butanol with that pKa of 18. The alkyl groups are destabilizing this negative charge, causing that pKa of 18 to be higher than that of methanol. But if I go over here and I put fluorine groups on those carbons, those fluorine groups are sucking the electrons away from the oxygen. That makes it so that the positive charge is already forming on that hydrogen, and it can easily come off. Another way to look at it is when the negative charge develops on this oxygen after losing the proton, these fluorines are sitting there and going, then sucking that negative charge down this way and through the bonds over to the fluorines. That makes this negative charge a lot more stable. It's not concentrated on one atom, but spread out into the molecule. Look at the pKa. It reflects that higher acidity. This is a much more acidic compound than the same compound that has just hydrogens in those positions. Here's some more examples. Look at chlorines on the carbon versus hydrogens on the carbon, and look at the pKa. This trichloroethanol has a pKa of 12.2. The ethanol itself has a pKa of 16, which is about the same as water. Here I have a phenol. Its pKa is 9.9. When I put a nitro group on, this is a very electron withdrawing group, and I put this nitro group on, what happens? The pKa drops. This is more acidic. If I were to put a methyl group on, remember methyls are electron donating, what would happen? You would get your pKa would go up because the methyl is electron donating and makes it less acidic. Now, using what you know, go ahead and order these by acidity, saying 1 is most acidic. Okay, if I look at these, I can see methanol and the trifluoromethanol. We know the fluorines are going to be electron withdrawing, so the methanol is less acidic than the trifluoromethanol. Then I look up here and I see that there's 3 methyl groups on the carbon versus 3 hydrogens here. The methyl groups are electron donating. That makes this less acidic. So the most acidic compound here is going to be the trifluoromethanol, and the least acidic is going to be the T-butanol. To deprotonate alcohols, you require a very strong base, much stronger than potassium hydroxide. That's not a strong enough base. To deprotonate an alcohol, you can take just plain sodium or potassium, and they actually will react with the alcohol group and make hydrogen gas. So the potassium is oxidized and the hydrogens are reduced, and we make this salt as a result. And this is a very effective and easy way to do it by just tossing a chunk of potassium or sodium into the alcohol, letting it bubble, and then you would have the formation of the alkoxide. Another way is to take sodium hydride and mix it with the alcohol. Again, hydrogen gas has evolved, and you make the alkoxide as the product. We can also use sodium amide. Right here is sodium amide. You mix that with an alcohol. The amide, this has a positive charge on the sodium and a negative charge on the amide anion. This grabs a proton from this, and it makes ammonia gas, which bubbles away, and then you have the alkoxide remaining behind. And then the last way is one way that we've already learned about in the alkyl halide chapter, is a Grignard reagent will react with any alcohol and deprotonate it and make this salt over here and the alkane. And the alkanes, if they're small enough, they become gaseous and also bubble away, and you're left just with the alkoxide. Phenols are more acidic than alcohols because of resonance. Once you form this negative charge here, it actually can resonate through the molecule in the benzene ring, and it stabilizes it. As a result, you can deprotonate phenols with either potassium hydroxide or sodium hydroxide. But remember, alcohols are not acidic enough to be deprotonated by potassium hydroxide or sodium hydroxide, at least not for quantitative deprotonation. There's a tiny bit deprotonated at equilibrium, but we essentially say that alcohols are not deprotonated by sodium hydroxide or potassium hydroxide. This is an effective way of putting a phenol into water by changing it into a salt. Phenols will react with sodium hydroxide to make a salt in water, and that makes that phenol water soluble, and you can pull it into water by making it salt that way. Electron withdrawing groups, this is a little bit more than what we want to get into here. This is more a second semester, but the resonance of electron withdrawing groups are actually what enhances the stability of a phenol, making it more acidic. So nitro groups are very effective at stabilizing negative charge and making phenols more acidic. I'm not going to expect you in this semester to be able to show the resonance of the nitro groups stabilizing negative charge, though.